I get to introduce our next speaker to you all, Gary Wolfe from Electra. Gary has received degrees from the University of Maryland and MIT, both in aerospace engineering, and has worked for 10 years on the development of advanced composites and metallic structures. Previously, he's a structural research engineer at Aurora Flight Sciences, supporting a wide variety of research and production programs, including NASA's Advanced Composite Consortium, Orion, the V-22, CH-53K, MQ-25, and DARPA X-65 programs. He's currently a principal structures engineer at Electra, where he leads the airframe team that is developing Electra's EL-9 ultra-short takeoff aircraft. And he also manages the structures and mechanical systems group. So presenting an introduction of the EL-9 aircraft and sharing how HyperX has been used to meet airframe challenges and optimize for weight, please welcome Gary Wolfe.
Thanks, JD. I don't think I need to introduce myself after a great introduction. So I'm Gary. I work at Electra. I'm the airframe IPT lead developing our 9-passenger hybrid electric stall aircraft dubbed the EL-9. You're going to hear a lot of some of the similar themes in this presentation as other small companies that have gone before me presenting. So Electra is a small startup, founded back in 2019. We're currently flying a two-seater tech demonstrator that had first flight back in 2023, and now we're working on this 9-passenger product. If there's one message I hope you take away from this presentation, it's the value that HyperX has been as Electra has defined our requirements, our assumptions, and started to mature this aircraft, and especially for a small company that doesn't have the legacy know-how, the past experiences, and that detailed documentation and mass property database to feed how we're going to design an airplane. HyperX has provided a lot of value there to help us answer questions quickly and move as a team to design this aircraft. So I'll skip over a lot of this since JD's introduction covered a lot of the important bits. I've used Hypersizer quite a bit over the years, from conceptual design to preliminary and detailed design, from small component level structures all the way up to full vehicle assembly, detailed analysis that was manufactured and tested. And now joining Electra, I've since changed hats and flipped roles, and I'm no longer the main POC running HyperX, and I'm on the other side of the table now as the airframe IPT lead that's driving the engineers to take out weight, move faster, reduce costs, and hit schedule. So enough about me. This is the EL-9 9-passenger product that Electra is developing to really pioneer direct aviation. So what that means, the EL-9 provides operational flexibility of a helicopter at less than fixed wing economics of other aircraft flying today. The EL-9 will be a Part 23 FAA certified aircraft, being designed to carry, I don't know if you can see here in the bottom left corner, a 9-passenger aircraft, hence the EL-9. Certified for single pilot operations, but with 2 crew stations carrying roughly 2,700 pounds of payload, a max range of roughly 1,100 nautical miles, a nominal takeoff and landing roll of 150 feet, a max cruise speed of 175 knots, and being a hybrid electric aircraft operating in a mostly quiet environment in a less than 75 decibel during takeoff. So I really flew through the major headline there of why the EL-9 matters. What are we trying to do? This is a ultra short takeoff and landing aircraft. And what do I mean by that is we are using blown lift to provide helicopter-like operational profiles. We've demonstrated that blown lift can increase our wing lift by 7-fold, allow takeoff speeds less than 35 knots, which allows us to have a ground roll less than 150 feet, or a total footprint of 300 feet. So imagine, a 9-passenger aircraft that can take off and land in an area the size of a soccer field today. Or what's shown there in that bottom right-hand picture, one of our desired missions that we're targeting is operating in and out of the Manhattan heliport. So how do we do it? So blown lift isn't new. It's been around for decades. Aircraft currently flying today have this capability, and even some of the engineers in this room have probably researched. I know at NASA Langley they have the opportunities and benefits of blown lift. What we're doing at Electra is really integrating three core technologies that provide unparalleled performance. The blown lift technology that I've already touched on that provides that 7x wing lift at very, very low takeoff speeds, less than 35 knots, and enables us to fly, take off in less than 150 feet and operate in a 300 by 100 foot ground footprint. And how do we do that? This is a hybrid electric aircraft. There's a turbo generator and battery packs that provide power to the electric motor. This hybrid architecture allows the turbo generator to be sized for cruise, and the batteries are really there to provide that power boost for that short takeoff and landing. Now, past stall designs have really showed that takeoff, in a short distance is relatively easy. Where it gets complicated, especially on the pilot, is landing, accurately, really over and over again, safely, repeatably. And in these tight environments that we're targeting, like that Manhattan heliport, you can see where it would be very critical to not miss your mark. And so that's where the EL9 is also going to incorporate a fly-by-wire system to really augment that pilot capability and enable all of this to work together and certify as a Part 23 aircraft and demonstrate this capability. Now, at Electra, we face a lot of the same problems that every, I think, new aircraft development faces. We don't have enough people. We have to move really quickly, and systems is constantly putting holes through our primary structure. So we are, like I've already mentioned, we are a startup. We have a really small team of extremely talented engineers. We're roughly 80 employees total across Electra. We are targeting on the far right there. You can see, I mentioned we started back in, 2019. It's just roughly 2020. We first focused on that 2-passenger tech demonstrator, which you can see there, that had its first flight in 2023, and is flying today almost, whenever the weather is great. So that started flying in late 2023, and then we're targeting a entry into service of 2029 for the EL9. So it's very much in development right now, and it will be certified by the FAA as under Part 23 regulations. I touched on briefly, but a major challenge of the airframe is the system integration. It's a hybrid electric architecture, so meaning, we have a turbo generator that's in the back, providing distributed electric to 4 independent battery packs. You can kind of see there, and then these are all powering the 8 electric motors that are distributed along the wing. So there's a lot of high voltage and propulsion integration throughout the airframe that we have to contest with. All these challenges lead to why HyperX. We're a really small team trying to move very quickly, and when you're trying to do that, you really need the right resources to answer all of the many questions. And so HyperX offers an industry-trusted tool that provides document analysis methods based off classical standards, as well as supports custom plugins to meet any of our particular requirements. So we don't have, we started with new and Bruin, and very quickly knew that we needed to come up with a better answer to feed our performance predictions and weight envelopes so that we can keep moving quickly and meet the certification deadline. So how do we do this? Well, historical data and legacy design practices are valid to a point. So this message has been touched on repeatedly today. Whenever you're starting a new aircraft development program, your early mass estimates and your early volume predictions and system architecture usually starts from the historical data, from those mass databases and the, your past experience. Electra is a very small company and doesn't have all of that, well-defined past examples to feed that. So we knew we really quickly had to move beyond the textbook, weight estimates and volume sizes, and start optimizing the airframe around what our objective was for the EL9. So how do we do that? Well, we started by evaluating a lot of our design assumptions, requirements, and our design, what we felt were the best practices against cost, weight, and schedule. And this allowed us to really pressure test, the criticality and impact of those different assumptions. What was actually driving weight? What requirements, could we change or could we, give up to allow us to meet our weight targets, or what was actually important to the program? And this really drove us to optimize for our design that went beyond just early parametrics and really started to redefine the box for the EL9 airframe. So going on in a little more detail, how do we do all of those steps previously? Is we've run a lot of trade studies on this aircraft, and I say we, Electra's partnered with Collier and JD and his team to do a lot of this analysis and feed the Electra team as we're progressing along. So we're using HyperX to evaluate the structural layout, assess the design and analysis requirements to rapidly mature beyond that parametric and really feed the design guides and the analysis plans. So, we don't have the super long detailed design guide from a past program where you would just copy and paste and start tweaking that to your program's needs. A lot of these documents we're starting from scratch, from day one, with first principles new and Brune, and then going through and running these trade studies to say, okay, we can do better. This is what the team needs to do, and how we're going to standardize the design to meet our whether it's a cost, schedule, or really manufacturability requirements. So we looked at a lot of different trades. You can see a number of here, whether it's material trades, we all around the aircraft evaluating metal versus composite for different parts, various stiffening concepts, trading for weight, the hat versus C versus Z stiffened composites, as well as analysis requirements. So you can see, we also looked at how does changing minimum gauge for metallic as well as composite and the impact on the damage and durability tolerance impact the aircraft cost and weight, as well as the buckling you can see on the right. And we looked at a large range of buckling criteria to see what was driving weight and around the aircraft and what assumptions we could tweak between the wing and fuselage and empennage and what were the right levels of conservatism to feed into the design at this stage so that we could be confident that we were designing an airframe that would in the end meet our objective. And lastly, producibility assessment. So throughout all of this, and I'll touch a little bit more on the next slide, we were constantly talking to manufacturing engineering to say, hey, can we make this? Can we do better? Sorry, August and Craig, I don't have any good pictures on this presentation of how the team took advantage of HyperXpert as well as the CAD generation tools, where we're feeding out that data and passing that along to the rest of the program team to say, can we manufacture this part? Can we manufacture it at the rate that we're looking for and at the cost that we're looking for? Once we get that thumbs up, that now feeds back into the design guide, into our best practices going forward as a company and as a team as we're maturing the EL9. And really want to harp on this slide here. This was this has been super critical and helpful for Electra as a team, which is, the plotting capabilities within HyperX, right? There are a few things more easily understood from across the entire program team than seeing your aircraft color coded with any kinds of data. What's shown here is the controlling load regime, right? So these kind of plots have been critical for us as a team to sit down and not just stress engineers and designers, but bring in the chief engineer, the loads group, the manufacturing and engineer, and look at these kind of plots and say, how can we improve this aircraft? How can we do better? Something that's unique, at least for me, is working on a brand new aircraft like this, where the customer is less defined, is we are defining the requirements and what is best suited to meet the mission that we're targeting for this aircraft. Now, of course, being a Part 23 aircraft, there are ASTM requirements of what loads we need to consider, but there's also requirements that we set that we want this aircraft to do. And so these kind of plots are critical for us to sit down and say, what are the driving load cases? What's increasing weight around the aircraft? Is that an appropriate load case? Is it certification driven, or is this Electra imposing a very strict requirement that we're trying to meet, that maybe we can loosen up that grip a little bit? And so these kind of plots have been really helpful as a team to shape the mission and objective of the EL9 aircraft. And again, then we can go back to the loads group and say, or flight controls, and say, hey, we need to make a change because this is driving weight, and I think we were being over conservative. Can we tune the flight control laws, or can we tune the takeoff and landing performance so that we can pull out weight out of the airframe? And so Electra is heavily using all of the plotting capabilities to really interrogate these models and reduce the overall weight of the airframe. And not just weight, I mentioned there cost as well. So like any certified aircraft, we are heavily focused on weight and cost and schedule of hitting that 2029 entering the service date. So, I touched on very quickly, but getting the manufacturing engineers in here as well and plotting not just loads, but from the HyperXpert plotting and looking at the stiffener spacing or stiffener heights or cross-section shape and all of that. And all of that feeds into our metrics that we're using to evaluate weight and cost and in the end justify how we're going to move forward maturing the design of this airframe. So I do want to cover some of the just high-level challenges and maybe some recommended solutions for interfacing with HyperX. I know everyone here is pretty much a user, and none of this should be a surprise. But as with any tool, users must recognize the challenges and master those design principles to avoid that classic garbage in, garbage out. When you're a really small team working on this, it's really hard to fall into this trough. New programs, we typically allocate time in the schedule to set up those analysis tools so they fit to the aircraft. Every aircraft presents unique challenges that the airframe stress and design engineer has to overcome, whether it's in our case, systems integration throughout the airframe, leading to very large penetrations or high temperature requirements, or every aircraft's unique. And so usually you start with in larger companies, you might start with an Excel template or Excel tool, or and copy and paste it for your program and start editing those tools. Electra doesn't, we don't have that legacy know-how, that massive folder of, past program A's approved analysis templates that you're starting with. So, this was a huge challenge for us, and one of the main reasons why I reached out to Collier to say, hey, we have a lot of questions, we have a lot of analysis. We really appreciate your help digging into this, as well as On the right, we've all seen the classic cartoon of, what an aircraft looks like when you design in a vacuum. With a small team running a very large aircraft assembly, I think it's really easy to fall into this kind of undesirable optimal design where the user just goes in and plugs in a min and max for every single variable, a super large sweep, and you just hit go. At the very end, you get a design, you show positive margins, everything's green, and you say, I just designed the whole airframe in 24 hours. You very quickly, once you really start digging into the weeds, you start looking in, you realize your design was shown here in the picture. It might show all positive margins of safety, but you go and show this to a designer or a manufacturer, and they might kick you out of the room. So it's really easy to fall into these kind of holes, and you kind of have to be aware of that with any kind of tool, but particularly I think HyperX brings its own challenges. So how do you avoid these two pitfalls that that I touched on in the previous slide, and really like a lot of the folks here have touched on today, you plan around incorporating and optimizing for HyperX from the beginning. That way you can fully leverage its structural analysis capabilities. So it's not just optimizing your airframe with HyperX, but you really need to set up your whole thought process from the get-go that you're going to use this tool. And that means decide at the beginning, plan out how you're going to build your GFEM, how are you going to work with the loads group, understand the limitations of HyperX, of the standard methods within the tool suite, what plugins do you need to go and develop, or just what are the limiting capabilities that you might need to then go and allocate time to develop plugins. And then also have a transition plan between phases. I know the Collier guys are preaching of using it from the beginning all the way to the end, and we just had a great presentation talking through taking it all the way to certification. But sometimes a program might decide that that's not the case, and so you need to know how you're going to transition between program phases, and it could even be continuing to use HyperX, so like from PDR to CDR, how are you going to transition your database to go to that next stage? Or are you going to transition out of the tool suite, and how are you going to do it? And lastly, developing a plan for interacting outside of stress. So how are you going to communicate with the loads group, with the designers, with the manufacturing and engineer? We've all touched on, there's a lot of data that HyperX provides to us as stress analysts. The hard part is figuring out how are you going to plot it or present it to the rest of the team so that it's meaningful. It's very easy to fall into, here's 100 slides with 100 screen grabs and give it to the rest of the team, and they're overwhelmed and can't digest it. I think the Collier team's doing a great job of creating tools like the HyperExpert, like the CAD generator that is meant to, I think, improve that communication across the teams. But I think this is, from the beginning to avoid some of those pitfalls I touched on the previous slide. It's really, highlighting on the right, plan the work and work the plan. So know from the beginning and, that you're going to use HyperX. This leads to my last slide. I ended with a fun, nerdy quote. With great power comes great responsibility. HyperX is a really great tool that's allowed Electra's very small team to optimize the EL9 airframe and provide inputs from across the program team. Allowed us to sit down, develop those design guides, develop those company best practices, our analysis assumptions, all through very detailed and well-documented trade studies where we've assessed not just one but hundreds of load cases and thousands of design concepts, and gives us a lot more confidence moving forward that we're going to close and meet our requirements. Thank you. Any questions?
Great presentation and great Spider-Man quote. If you go back 2 slides, a quick question. You kind of touched on this with HyperExpert and the CAD import and export, but you said that you plan and optimize around HyperX, and that you develop a plan for interacting with those outside of stress, which is often very important, and we miss it sometimes. I was curious if there's any specific additional features that you felt beneficial from HyperX for interacting with those outside of stress, or dare I ask, any features that you wish were in it to help with that capability?
Good question. I think I showed a good picture of the loads plot. That's been super helpful interfacing with groups like the loads group, because they care a lot about that. Showing that kind of picture to a chief engineer or a flight physics person. I mean, the amount of value I've gotten was, wow, this is great. Now we know how to turn the wheel. I would say the hardest folks to interface with sometimes are the manufacturing engineers, right? And trying to relay, which I know the CAD generation tool is trying to improve the communication with designers. I think it's how can we add on to that to better communicate with the manufacturers. I think the EL9 aircraft is a primarily metallic structure. HyperX has a lot of composite capabilities, a lot of visualization for developing that soft tooling and going to the layup techs or the manufacturing guys and showing this is how I'm going to drop plies. On the metallic side, it's how can we do something similar to present the metallic metadata so that, hey, can we physically manufacture this metallic part?
Thank you.
Sweet. It was easy.